Hello students, welcome to the class. So today we will do the Thermodynamics NCERT Theory Part 9, in which we will cover the section 5.6. So this is the disclaimer. Our objective would be to study spontaneous and non-spontaneous process. So this is basically a division of the process on basis of its ongoing process, right? So how does a process exceed or proceed? So if it is exceeding by itself, then we call it as spontaneous, and if it requires some external agency, then we name it as non-spontaneous. Now there are certain examples of it. We'll try to understand the same with the help of those examples. If we are done with that thing, then we will try to define criteria for the same, which is spontaneity. And that criteria would be like your entropy, which is again a new thermodynamic state function. And we'll use this to define the spontaneity, or I would say we'll try to define the spontaneity with the help of entropy. So the first topic would be, according to the NCERT, will be spontaneity. Then in that we will see that whether the enthalpy is a criteria for spontaneity or not. We will check it with different conditions. If it is good, then we'll go on with the enthalpy. So the conclusion will be that enthalpy will not work for the description of a spontaneity. So we'll have to define a new state function, which is entropy. And the second law of thermodynamics will be introduced at the same time, which will be again related to the entropy. And lastly, we'll see the third law today. Okay, so we'll see both the second law and the third law, and plus the entropy part. Okay, so let's start our discussion. First, we will try to understand what is a spontaneous process and how do we decide that a process that is being carried out is spontaneous or not. So spontaneity, for a reaction to be spontaneous, the definition is that it should proceed without the existence or assistance of external agency. Now here is a small twist in this. Suppose you are considering the combustion of a hydrocarbon, right? Now this process would look like that it will need an external agency, like a small flame or something like that, but in reality it is a spontaneous process. So basically you can add a line in spontaneity that the reaction will proceed by itself, either by assisting it in the start or not assisting in the start. So you can take several examples where you need a small jerk to just start the reaction or kick off the reaction, and then the reaction will go on by itself. So that reaction will be also considered under spontaneous process. We can consider more examples of the same. So our daily life example would be like water flowing down the hill. So due to the greater potential of water at a higher height, it has a hidden energy inside it, and that converts into kinetic energy while the water flows down the hill. So this is what a spontaneous process. We don't have to do anything, it pours down by itself. Next is the expansion of a gas. So it's very easy to understand this concept. So whenever you spray perfumes in your room, right? So initially that perfume is being stored inside the bottle in which the perfume is being bought. As you spray that perfume, the gas that comes out of that perfume quickly spreads throughout your room. So here the gas is expanding by itself and we don't have to do anything. Okay, you are nothing doing extra in it. Only you are pushing the, I would say, the nozzle to bring out that gas. So here you are doing, you are jerking off the reaction in the start. Now what are the characteristics of a spontaneity? So the first is, spontaneity is not related to the rate of the reaction. So if you are judging the spontaneity of the reaction, then you are in no place to deduce the rate of the reaction. So that will be studied in a different branch. You will go to class 12th, or when you will study the chemical kinetics chapter. In that chapter you will look upon this rate of the reaction, and our whole thermodynamics is not concerned about this topic at all. It is only concerned that whether the reaction will happen or not. So that is your spontaneity. Okay. Second thing, A spontaneous process is always a irreversible one. How can we understand it? So think of the water flowing down the hill. Is it possible that your water can flow back to the top? No, it's not possible at all, right? So it is not reversible. It can't go backward. For that reason, you can take many more examples in the same way, and you will see that all the spontaneous processes that you are observing will be a irreversible one. And lastly, if you want to reverse a spontaneous reaction, suppose in any case, then you have to do it by some external agency. And that is not the definition of reversible reaction at all. Because a reversible reaction can be reversed by a small external agency, but here you have to apply it regularly. Like if you have to bring the water back to the top hill, certainly you will take the water in the bucket, in any bucket or any container, and you will just lift it up with any pulley or something like that to bring it back to the top. So basically you have to apply force constantly to bring it back on the top. Clear? So this is the basic difference between the spontaneous and the non-spontaneous process. Now question arises, we were interested in the spontaneity part. Do we have a state function for defining the same? So let us start with enthalpy and see whether that enthalpy is a deciding factor or not. Now there is a general perspective that if your spontaneity is being described, then it is described in terms of energy. How? If your system is going from a higher energy to a lower energy during a process, that means your process is spontaneous. And that's the only criteria enthalpy thinks of. Got it? Again, I'm repeating it. So suppose if a process is going, and in that process, your system is going from a higher energy to a lower energy. And we are telling that, okay, this is the only criteria for defining the spontaneity. Clear? Now this same thing is said by enthalpy change, because enthalpy change is nothing but the change in energy at constant pressure, right? But this is only true for some of the processes. Like if you consider the water flowing down the hill, if it is going from a higher height to a lower height, so its potential energy is decreasing. Similarly, you will often see many of the things like your elastic rubber in which the potential energy is stored. If you just stretch it, it will again go back to its original shape because of that higher energized state. So these are the examples that are proving in a way that, okay, the decrease in energy can be a reason for spontaneity. But the question is that, is it the only part that we have to worry about? We will clear that with few more examples. Now this led to the idea, this whole discussion led to the idea that, okay, in a way, spontaneous processes are those processes in which the energy is released or a system goes from higher to lower energy. Now, what do we call those type of reactions in which the energy is released? Obviously, we call it exothermic reaction in terms of enthalpy. So, can we say that every exothermic reaction is a spontaneous one? Let us look at some examples. So, we are still in our mid path. So, first, we will look at a reaction coordinate. So, here you can see two parts, reactants and the products. Okay. So, here is the reactant, and the reactant's energy is represented by, or the enthalpy is represented by HR, and the enthalpy of the product, or the total enthalpy of the product, is represented by HP. So these are the 2 points. Now if you try to calculate the difference in their energy, let us assume that that energy is delta RH, or the reaction enthalpy. It will come out to be negative because the enthalpy change is equals to product minus reactant, and product is at a lower energy. Therefore, this reaction is exothermic. So you must know how to represent a given reaction in terms of reaction coordinate. Now, if this is clear, let us look at some real examples. So first is synthesis of ammonia, and in that we are seeing that the enthalpy change is minus 46.1 kilojoule for per mole of ammonia. Since this reaction is having a negative reaction enthalpy, therefore it is a exothermic reaction. We can look at one more example where we are seeing the production of hydrochloric acid, and here also the value of enthalpy change is negative, again a exothermic reaction. Now, what we can conclude from here, that in both of these processes, the energy is released because your reactants, which are nitrogen and hydrogen in the first case, and hydrogen and chlorine in the first case, are going to a stable product, which is ammonia and hydrochloric acid respectively. So therefore, we can think of decrease in energy as a possible driving force for a spontaneous process. Okay, because all this process that I mentioned right now, they are spontaneous in nature. And the reason that we are giving for now is your decrease in energy or your exothermic process. But there is a contrast to this situation. Let us look on that situation now. So that situation is related to some endothermic process. Here you can see on the right hand side, we have a reaction coordinate for the endothermic process, where the reactant is going from a lower energy to a higher energy to get into the product. Therefore, energy will be absorbed in the whole process. We can have the example of the same, like your formation of nitrogen oxide and your carbon sulfide. But the problem is that although these reactions are endothermic, as you can look at the positive value of enthalpy change, but they are a spontaneous one, right? So our vision, which was to prove the spontaneity on the basis of enthalpy, is totally shattered. Why it is shattered? Because we are seeing a positive value of enthalpy, that is endothermic reaction, and still we have observed in experimentally that this reaction is what? It is spontaneous. So what we can conclude from here, that enthalpy can be a factor for deciding the spontaneity, but it is not the only factor. Now what's the factor? Because we are unaware about it. Let us move on to a more solid example to exclude the enthalpy from spontaneity. So I would not say it excluding it. I would say that I will move the total dependence. See, this is our general perspective. So it is being discussed here because we think in general that if your body is going from a higher energy to a lower energy, that means that process is spontaneous, and that's the only way we can do a spontaneous process. But with the help of the endothermic reaction, which is spontaneous in nature, we have proven that your enthalpy is not the only deciding factor. We will take a much more concrete example and a concrete case to justify the same. And what is that case? So that case is for delta H is equals to 0. So for some reactions, we will observe that there is no enthalpy change during the reaction. Okay, so delta H is equals to 0. But still your reaction is spontaneous. Got it? So what I am saying is that during your reaction, no heat is released and no heat is absorbed. But still the reaction is spontaneous. Can we take some examples of it? We have already seen those examples. First is your gas diffusion. So generally, when you keep two gases, right, in two compartments, and if you remove the partition between them, they will mix automatically without any external agency. So what you can say, that this diffusion of gas is a spontaneous process, and in this process almost the enthalpy change is 0, right? So we can say that mixing of or diffusing of two gases is a spontaneous process, although it is having a 0 enthalpy change. Now what we can conclude from here, that decrease in enthalpy, finally we are writing it, that decrease in enthalpy is not the only criteria for spontaneity. And at the same time, we are defining a new factor here. What is that factor? That factor is disorderness. So you will see that once your gas is diffusing, it is moving to a much more chaotic situation. We will look on to that with the help of a diagram, and that chaotic or disorderness is now the new criteria which will help us to decide the spontaneity. So here is a diagram for the same. You can look that we are keeping two types of balls. On the right hand side we have white balls, on the left hand side we have black balls. and in between we have a blue partition. As soon as we remove this blue partition, you can look on the right hand side that we are mixing these two gases without any external agency. Now in this process, the enthalpy change is almost zero, but still this process is going on it by itself. Now what are the factors that we can consider here? I said it that they are initially separated. Now what is the conclusion of this initial separation? We can say that it is a ordered situation. Okay, it is a much ordered situation as compared to the right one. How can we understand the same? Suppose you are able to pick the balls, right? Since atoms are bigger enough so that you can pick them. If you try to pick the ball in the first situation before they are mixing, suppose you are moving it from the left hand side, then you are certain that you will get a black ball. There is no question in that, right? Similarly, if you pick a ball from the right hand side, you are certain that you will get a white ball. But if you do the same after removing the partition, you are almost uncertain that which ball you will pick up, right? So in this case, you are not able to see the balls, you are just picking it up. You must have seen a game in which you are putting your hand in a dark box and picking out something similar to that. So in the second case, you are very uncertain that which ball you will get in your hand. Therefore, this system that we are getting after removal of partition, it is a much more chaotic one and it is less predictable. And that disorderness which we are getting to this chaotic situation is the major factor for the process of diffusion to go on it by itself. Or we can also say that your system is going to a much more random situation. Clear? So we are moving on to a new factor, which is randomness, which will now decide our spontaneity of a given process. Got it? So we have written a very strong line here. Tendency towards increased disorder is a driving force for spontaneity. Now, at this point, we need a state function to describe the randomness, and that state function is inentropy. So what is inentropy? It is basically the measure of the degree of randomness or disorder in a system. And what are its fundamentals? It is a state function first of all, again, and if you are having a higher disordered system, means you are having a higher inentropy. Now, on the basis of this, can you say that which of the states, so we have three states, solid, liquid and gas, so which of the state will have a much more disordered situation? So your answer would be obvious. First of all, if I consider solid, it is in the lowest inentropy as compared to any other two states, right? So solid is in the lowest inentropy. Then we have what? A liquid, and lastly we have the gas. So gases are present as the highest inentropy. So this is a very, very important conclusion. If you want to describe the inentropy for the same element but in three different situations, or you can take different elements also or different compounds also, and if you want to describe the inentropy for three different states, then the gas will have the maximum inentropy, then the liquid, and lastly will be your solid. Now, what we can conclude from here, from our overall discussion, that if your reaction is resulting in an increase in disorderness, that means your inentropy is increasing, right? Because inentropy is nothing but your randomness. So if your system is moving to a more disordered situation, means the inentropy will be increased. Got it? So can you think of an example where you are going from one state to another during a process? So it can be physical and chemical and both. And what would be the change of inentropy? Obviously, you can take the example of phase transformations. So whenever you go from a solid to liquid state, your entropy will increase, and from liquid to gas state, the entropy will increase even more. So this is very, very important conclusion. Now, what is the relationship between spontaneity and heat and temperature? So to describe the spontaneous in terms of mathematical equation, we need some dependency on some variables, and those variables are heat and temperature. So it is seen that if you are observing heat, right? So if you are adding heat to a system, then its molecular motion will increase, right? Its molecular motion will increase and your system will become more and more random. So what you can say, that is spontaneity or inentropy. So I would specifically say inentropy. So inentropy is directly proportional to the heat supplied because it increases the molecular motion. How is the molecular motion increasing? Because when you supply heat, you are supplying energy. Therefore, molecules will move with a much more higher speed. Then let us look at temperature. Now think of a situation. Suppose you are taking ice, right? You are taking ice and start to heat it. What you will observe, that your ice shows quick change in your temperature, right? Or quick change in your state. It starts to convert easily into the liquid form if you even supply a small amount of heat. Why is it so? Because your system is at a lower temperature. So your ice is present at 0 degrees Celsius. Therefore, when you apply heat, it quickly changes its states. So what you can say, that the effect of heat supplied is more prominent at lower temperature. Or you can also say that randomness increases more easily at lower temperature. Therefore, your spontaneity or the inentropy, I would not say spontaneity, your inentropy is inversely proportional to the temperature. And you can apply the same logic to high temperature. What you can think of? You can think of water. If you supply heat to water, it will not start to convert into liquid phase, into gaseous phase easily, right? You have to supply more and more temperature. So that takes time. So you have to supply more and more energy to increase its randomness because it is at a higher temperature. Therefore, we can conclude from here that low temperature is good for increasing the randomness and more amount of heat is good for increasing the randomness. Therefore, we can say for the relation between inentropy, heat and temperature, that your inentropy change is directly proportional to the heat supplied, and that also at reversible situation. So this is very important part of the say your definition, right, or the mathematical equation, that inentropy change is directly proportional to the heat that is supplied reversibly, okay, and it is inversely proportional to temperature. We can just combine both of these situations and write our final equation, which is delta S is equals to Q reversible by T. So this is very important equation, and the most important part of this equation is your heat that is supplied, it must be supplied at reversible situations. Now why we need to verify here, or why we need to put a constant that this is only good for the reversible case? Because heat is a what? It is a path function. If we supplied it in a different way, then we will get results in different way also. Now this formula is only applicable to reversible process. Therefore, your heat should be also supplied in reversible manner. I think this part is clear to you. Now we will try to define, if you are clear about this inentropy, we will try to define the second law of thermodynamics. What does it say? It says that if you want to keep a process spontaneous, then the inentropy of the total universe should increase, right? Total universe means system plus surrounding. So you have to consider the whole universe rather than the system. Now we can write it mathematically, that what will be your change in inentropy, total change in inentropy, it will be change in inentropy with respect to system plus change in inentropy with respect to surrounding. So we have two parts, and for a process to be spontaneous, your delta S total should be greater than 0, right? So this was our say conclusion. So here it is written, delta S system should be inentropy change for system, delta S surrounding is inentropy change for surrounding, and delta S total is inentropy change for universe. Now if your inentropy should increase overall, therefore you can also say that the total inentropy, that is system plus surrounding, should be greater than 0, right? Now from here, let us consider an example. Suppose for any reaction, if you are telling that what will be the situation before equilibrium, how will the system proceed? So I have told you that for the system to proceed, the total inentropy change should be positive, right? Therefore, we have written it as delta S total is greater than 0. Now, what can be the next situation? After equilibrium, what will happen? So, after equilibrium, there will be no change in inentropy, right? This is very clear, I guess, because initially, when your system is not in equilibrium, it starts to move towards equilibrium. Now, I have not introduced to you with this term, so I am telling it about it. So basically, equilibrium is a stage after which a reaction will not proceed, right? For every spontaneous process, there is a stage where it reaches, and after that, it is not proceeding further. So that stage is defined as the equilibrium stage. Now it is seen that since your system is going from one state to the second state, and it is moving spontaneously, that means the total inentropy must be increasing. And if it is increasing, means the final part will be greater than the initial part. So the inentropy change will be greater than 0. And after equilibrium, what will happen? The system will not change any further. So inentropy will not change, and hence the change in inentropy will be 0. So not the value of inentropy is 0, but the change in total inentropy is 0. So what can we conclude from here? There are two situations, including the equilibrium and the non-equilibrium part, that for a spontaneous process, if the system is proceeding by itself, the inentropy will first start to increase and it will reach a maximum point. And as soon as the system reaches the maximum point, which is the equilibrium, the change in inentropy becomes 0. Therefore, we can say that the inentropy is a important factor. I would say it will the only factor that could decide the spontaneity of a given reaction. But the problem is that we have to look upon the total inentropy and not the system itself. So that's the problem here. We will see this thing also. Now moving on further, let us try to define it for the universe. So we have seen that we have a 0 case and we have a greater than 0 case, right? Now this 0 case that we are seeing, it is applied to a certain process. You know that if a system is in equilibrium, means the system can be proceeded in both the directions, or it is a reversible one. And we have already seen that in the case of equilibrium process, there will be no change in entropy, and that same is applied for the reversible process also. Let us try to just dictate, or I would say derive the same. So consider an isothermal process, okay, and the process which we are considering is a reversible process, right? Now in the process, the system is absorbing heat from the surrounding, and it is happening at temperature T, because we know that the process is isothermal, so we have fixed the temperature at T. So what can be said about the change in entropy for the system if it is absorbing Q amount of heat? So plus Q reversible, which is your heat absorbed, divided by T. So this is your change in entropy for the system. Now what can be said for the surrounding? So if your system is getting plus Q reversible heat, that same amount of heat is lost by the surrounding. So we can say that delta S surrounding is equals to minus Q reversible by T. We have to just reverse the sign of plus Q to minus Q. Now, what is the total entropy change? Right? So we can, why we are applying this formula again? It's a reversible process, so we can apply this. Okay. Now, if you put both the values, Q by T plus minus Q by T. Here I have dropped the notation of reversible for heat change, so you don't have to worry about it. Now next, what will happen? For a reversible process, the delta S universe will come out to be 0, or the total entropy change will all be equals to 0. Next, entropy change for ideal gas. Now there are certain formulas for different conditions, and we will look on to one. Suppose we are doing a small change in internal energy by doing an infinitesimal change in the system. So how do we represent the first law of thermodynamics? It will be du is equals to dq reversible plus dw. So this is the equation. Now let us divide the above equation by T. What we will get? du by T, dq reversible by T plus dw by T. Why I am writing it D? Because we have done a small infinitesimal change. So for small changes, we represent it by dw or du, right? Then how can we replace it? We know that u is equals to qv and qv is equals to cv dt, ncv dt, right? So instead of du, we have written it as ncv dt. What about dq reversible by T? Again, we know this about the same, that dq reversible by T is nothing but your entropy change, and your work done is minus pdv, right? So what we got, ncv dt by T is equals to ds minus pdv by T. Therefore, replacing the pressure with nRT by V, we get the final equation as ds is equals to ncv dt by T plus nRdv by V. So this is the entropy change for a small infinitesimal change. But if you want to calculate it for the whole process, what you will do? You will simply integrate it. So we will do the same. We will integrate it with the proper limit. So for entropy, we have S1 to S2, temperature we have T1 to T2, and volume we have V1 to V2. If you integrate it, you will get your final equation as S2 minus S1, which we have represented as delta S, is equals to NCV ln T2 by T1 plus NR ln V2 by V1. So this is our final equation for the entropy change for ideal gas. Now, let us look on to one more entropy change, which is related to phase transformation. So suppose you are doing a phase transformation from alpha to beta. So these are the two phases. So it can be anything, solid to liquid, liquid to gas, gas to solid, right? And you are doing the same at temperature T and pressure P. Now, the formula which is defined for calculating the entropy for this phase transformation is delta S transformation is equals to delta H transformation by temperature at which the transformation is taking place. You will understand the same with the help of a quick example when you will see different transformations. Before that, let us define the terms that we have seen. So delta S transformation is what? It is the change in entropy during the phase transformation. What is delta H transformation? It is the change in enthalpy. And lastly, your T transformation is the temperature at which the transformation is or the transition is occurring. So let us define it for different situations. For the first situation is the fusion one. Now in the fusion case, we are seeing the entropy change related to melting. So what we can write? Delta S melting is equals to delta H by Tm. Now here we have written the temperature as Tm. So what is Tm here? It is the melting point of substance. Suppose you are considering it for water. Then what you will write in place of Tm? You will write it as 273 Kelvin. Then next we have for vaporization. Again, vaporization occurs at boiling point. So the change in entropy for vaporization is equals to enthalpy change during vaporization by boiling point of substance. And lastly, we have sublimation. Again, the same thing. The thing which we have to do, the only thing which we have to do is to replace the temperature. So here the temperature that is mentioned is the temperature at which the sublimation will take place. Okay, I hope you got my point. Now let us describe the last thing, which is absolute entropy, and with that we will also try to define the third law of thermodynamics. Now, to understand that, we have to first know that what is molecular motion and what is its relation with entropy. We know it very well that molecules are always in a random motion. So the motion can be translational, rotational, vibrational, depending on the molecule that we are dealing with. But one thing is for sure, that it is always in the state of motion if you are observing your body at normal temperature. But it is seen that as the temperature goes down, this movement becomes slower and slower, and at last, as this temperature is completely gone to the 0 Kelvin, then at that temperature the movement stops. Now the opposite can be seen for the same case. If you increase the temperature, this motion will become more and more vigorous, and more vigorous means it is moving fastly, or you can say the randomness is increasing, or you can say the entropy is increasing. So what we can say that on lowering the temperature, the entropy decreases, and we know it for sure. Because if you are decreasing the entropy of any system by lowering the temperature, means your system is losing heat, right? So that's the only possibility. Your system can go to a lower temperature. So if it is losing heat, we know it that delta S is directly proportional to heat. So if it is losing heat, the entropy will decrease. Okay. Now it is seen that, so this is just a hypothetical case. We have tried our best to reach this absolute zero, and there are very few cases in which we are successful. And in those cases only, the motion of the molecule is restricted. So it has no further motion, and we say that, okay, this is the pure crystalline form of that substance which we see at 0 Kelvin. Got it? So this is very, very important. And this is the third law of thermodynamics. Very simple. And due to perfect atomic and molecular order in a crystal at 0 Kelvin, we can say that entropy is also becoming 0. Now, let us try to summarize all of those that we have dealt till now. First, we saw that spontaneous processes are those which occurs without any external agency. And in that process, the total entropy, including the system and surrounding, increases. The second is, entropy is what? It is the measure of disorderness. Higher is the disorderness, greater is the entropy. Third thing we saw is the second law, which says that if you are looking at the universe, then it is always involved in some process. If it is involved in some process, means it is going through a process in which the entropy will increase, right? Because no process in the nature is reversible in nature. Okay, and if the process going on in spontaneous way, therefore, and the system is also not at reversible condition, therefore its entropy must be increasing. So we can say that our universe is moving to a situation where its entropy will move further and further. Then next we saw formula for the calculation of the entropy. First is Q reversible by T, and second is delta H vaporization by T, where so we can have different situations. So it can be vaporization, melting, fusion, depending on the transformation that we are looking on. And the third law is that for a perfect crystal where the temperature is reached to 0 Kelvin, the system has a 0 entropy. So this was all for today's lecture. Thank you. I hope you enjoyed the session.